So the next step, the second step in the design is to determine the location of the far off poles, namely P4 and P5. Before we do that, let us first redraw the root locus for the system that we are in the process of designing. So we have marked out the 3 plant poles P1, P2, P3, which are at 0, -1 and -2 respectively, and we wanted the dominant dynamics to be located at -1.5 plus -2j, and we have now discovered where we have to place our 0, z and z bar. So we have discovered the distance and the orientation of z and z bar with respect to the point PCL naught, which is the point at which we want our closed loop pole to lie. So this is PCL naught, that is PCL naught bar. Now we also have 2 far away poles, namely P4 and P5. We have not yet fixed the positions of these poles. It turns out that it is not an arbitrary choice, and there is some caution that needs to be exercised while choosing the positions of P4 and P5. So the second step in the design is to determine where we can place P4 and P5. But now that we have placed the 0 z and z bar in the complex plane, let us briefly sketch the approximate root locus for this system. So we would have one branch of the root locus starting at P1 and another branch starting at P2, and both these branches meet at some point on the real axis and then break away into the complex plane, and these branches will eventually go through the point PCL naught and finally sink into the 0 z, and the other branch will sink into the 0 z bar while passing through the point PCL naught bar. So this is going to be the fate of 2 of the branches of root locus. Then we would have one more branch starting from the point P3, namely at s is equal to -2, and heading off to the left of the point P3. Now since we have 2 poles P4 and P5, we would have one branch from this combination also heading off towards the pole P3, and these 2 branches are going to meet at some location on the real axis, and then they are going to have another breakaway, and these 2 branches have no zeros remaining for them to sink into, and therefore they break away and head away in this particular manner, and there will be a particular gain at which they cross the imaginary axis. So if the gain of the overall open loop system is more than this particular value, then one pair of poles are going to lie on the right side of the imaginary axis, or we would have an unstable system on our hands. Now altogether we have 5 poles, so we need to have 5 branches to the root locus, and hence the 5th branch would start from the point P5 and head towards its left towards s is equal to -infinity along the real axis. So for the closed loop pole on the branch starting from the point P5, there is no concern associated with stability. However, for the branches that start from P3 and P4 and which meet at some point and then head off into towards the imaginary axis, there is a real concern as regards the stability of the closed loop system. In particular, what we need to make sure of is that when the plant gain reaches its maximum value, so when the plant gain goes to 3, then where would we have the closed loop poles? We would have one pair of closed loop poles on the first pair of branches. So we would have the closed loop pole at PCL max and PCL max bar. So this will be where the first pair of closed loop poles would be located, and by design they would be located in such a manner that it would be well within the prescribed variation of 0.4 units from the point PCL naught. Then we would have one more pair of poles, closed loop poles, and they would lie on this branch. So I shall call that pole as Q and its complex conjugate as Q bar. So we would have one pair of poles on the branch that emanates from P4 and the other branch that emanates from P3 and breaks off towards the imaginary axis, and these two closed loop poles are not guaranteed to be stable, because it is very likely that when the plant assumes its maximum gain possible, it is very likely that the point Q is on the right half of the complex plane, and thus our closed loop system might become unstable. The final closed loop pole will be located to the right of the point P5. So the final closed loop pole will be located somewhere here. I shall call that closed loop pole as R, and that is something whose stability is not of concern to us. It neither dominates the dynamics nor causes problems with stability, so that is not of any concern to us. So what we really need to be worried about now is the fate of the pole at the point, closed loop pole at the point Q. So we need to make sure that when the open loop gain of the system assumes its maximum value, which happens when the plant gain assumes its maximum value, the point Q, the closed loop pole position Q, is at most on the imaginary axis and never to the right of the imaginary axis. So that is the second challenge that we have to take up, and that is going to be part of the design in the second step. Now the root locus that I have drawn here is really not to scale. That is because we have assumed the distances of the points P2, P3, P4, P5 and so on from the origin are all nearly comparable to one another, so that they can all be shown on the same graph. However, as we discussed, we have chosen to place the points P4, P5 very far away from the origin. Therefore, what would be a more realistic root locus would be something that looks like this. I am redrawing the same root locus that I have drawn here, but by paying slightly better attention to the scale, the typical distances between the points P1, P2, P3, the points Z and Z bar and the points P4 and P5. So we would have the real part of S versus the imaginary part of S. Now since the points P1, P2, P3 and Z and Z bar are very close to the origin, I shall indicate them by 3 cross marks, each of which represent the points P1, P2 and P3, and 2 circles which represent the 2 zeros Z and Z bar. All these are near the origin. In contrast, we would have the point P4 and P5 to be very far away from the origin. So this is probably a more realistic representation of the typical distances of these poles and zeros from the imaginary axis. So if we were to redraw the root locus that we have just drawn here, we would have one branch starting at P1 and one branch starting at P2, and they both sink into the 0 Z and Z bar. We would have one branch starting at the point P3 and another branch starting at the point P4. These two collide somewhere on the real axis, and then they break off into the general complex plane and eventually cross the imaginary axis at some particular point. And then you have another branch which is on the, which starts from the point P5 and heads towards the negative real axis, and the closed loop pole on that branch will not pose any problems to us as far as stability is concerned. The real problem would be posed by a pole Q on the branch that emanates from the points P4 and P3. So this is the point P3, this is the point P4. We are really concerned about the stability of the pole Q. Now if we were to be located at the point Q, then we would have the root locus equation, namely 1 plus k times Cp at the point Q to be equal to 0, which means that k will be equal to minus 1 by Cp at the point Q. So if we were to once again recollect the geometric interpretation of the term 1 by Cp, this would essentially be equal to S times S plus 1 times S plus 2 divided by times S plus P4 times S plus P5 divided by S plus Z times S plus Z bar and this whole thing gets multiplied with -1. So that is k, and this is evaluated at the point q. Now if we recall the geometric interpretation of the complex number s evaluated at the point q, it essentially is the complex number p1q. So the first term therefore will be equal to p1q, and the second term would be the segment. So s plus 1 evaluated at the point q will essentially be equal to p2q, and s plus 2 will be p3q, and likewise we would have p4q and p5q as the other distances. And in the denominator we have s plus z and s plus z bar, so that would be zq and z bar q. So these would be the terms. Now if you recollect, we have chosen to place p4 and p5 very far away from the origin, and what that implies is that the point q therefore is also very far away from the collection of poles p1, p2, p3 and the zeros z and z bar. So since the point q is very far away from this collection of poles p1, p2, p3 and z, z bar, what happens is that the length p1q and p2q and p3q are very nearly identical to one another. The angles subtended by p1, p2, p3 at the point q will also be very nearly equal to one another, and so will the angles subtended by zq and z bar q. All of these subtend the same angle very nearly at the point q, and all these distances will very nearly be equal to one another. So here we have 3 poles near the origin and 2 zeros once again located close to the origin and very far away from the point q. So therefore if I am sitting at the point q, this collection of 3 poles and 2 zeros will essentially look like a single pole to me, because the effect of 2 of the zeros cancels the effect of 2 of the poles, namely p1 and p2's effect gets cancelled both in magnitude and phase by the term zq and z bar q. So for all practical purposes I can replace the 3 poles and 2 zeros near the origin with just a single lumped pole. So in this schematic here I have now replaced the 3 poles and 2 zeros which were near the origin with a single lumped pole, which is how this combination would appear for the point q, which is on the branch of the root locus that is very far away from this combination of poles and zeros. Now we want to make sure that when our plant's gain assumes its maximum value possible, the point q does not lie on the right half of the complex plane. At most it should lie on the imaginary axis, although strictly speaking even this is not really desirable. It should in general lie slightly to the left of the imaginary axis, so that we still have a stable closed loop system on our hands, or in other words a system all of whose closed loop poles are on the left half of the complex plane. So we can get our point q to be arbitrarily close to the imaginary axis but not really cross the imaginary axis when the overall gain of the open loop system assumes its maximum value. So in this situation, when the overall gain is at its maximum value, let us assume that the point q is located near the imaginary axis, arbitrarily close to the imaginary axis. Since the point q is a point on the root locus, we should have the magnitude criterion and the phase criterion of the root locus to both be valid at this particular location. So let us first apply the phase criterion. What it indicates is that the phase, the angle subtended by the poles PL, which is the lumped pole at the origin, the effective pole which is the combination of the 3 poles and the 2 zeros that were located close to one another. So this one effective pole and the 2 far away poles P4 and P5 put together should subtend an angle of minus 180 degrees at the point Q, since the point Q is a point on the root locus. So what this indicates is that the angle of QPL plus the angle of QP4 plus the angle of QP5 should be equal to minus pi or minus 180 degrees. Now we have not yet decided where to locate the points P4 and P5. In fact, we do not know what distance they need to be from the origin. For the moment, let us assume that these two are coincident poles. In other words, the location of P4 is the same as the location of P5. Since we have two coincident poles, our problem now boils down to determining the distance of these closed loop poles, which I have indicated by the symbol L, from the origin. If we can determine its distance, then we can determine where to locate the closed loop poles and what their exact numerical values will be. So since we have assumed them to be coincident, we would have the angle of QP4 to be the same as the angle of QP5. So we would have angle of QPL plus the angle of QP4 times 2 should be equal to minus pi. Now what is the angle of QPL? Since PL is a lumped pole near the origin and the point Q is a point that is very close to the origin, we can note that the angle subtended by this complex number QPL with respect to the real axis is actually equal to 90 degrees. So this angle is 90 degrees. However, since we have a pole near the origin, the contribution of this pole is going to be the negative of this angle. So QPL is therefore going to be equal, angle of QPL is therefore going to be approximately equal to minus pi by 2 radian, or in other words in degrees it will be minus 90 degrees. This is because the point PL is situated close to the origin and we are considering the case when the point Q is very close to the imaginary axis but not to the right of the imaginary axis, when the overall loop gain of our system has assumed its maximum value. So if QPL is approximately minus pi by 2, then this equation here indicates that the angle of QP4 should be equal to minus pi plus pi by 2 divided by 2, and which essentially comes down to minus pi by 4. What this indicates is that the coincident poles P4 and P5 should both subtend an angle of 45 degrees or minus pi by 4 radian at the point Q. So this angle should be 45 degrees. So since we have this angle here to be 90 degrees and this angle is 45 degrees, so in this triangle that has been formed by the point PL, the point P4 and the point Q, we would have the other angle to also be 45 degrees, which implies that this triangle is a right angled isosceles triangle, and that in turn implies that the line PL P4 should be equal in magnitude to the line PL Q. So this also therefore should be of the same magnitude L as the distance of the point P4 from the origin. Although the schematic that I have shown here does not indicate that these two lengths are the same, our calculation reveals that because of the particular distribution of the poles in this particular system, at the location Q the points P4 and P5 should each subtend an angle of minus 45 degrees. Now that we have determined the angle that the faraway poles subtend at the location where the root locus crosses over from the left half plane to the right half plane, let us now apply the magnitude criterion of root locus at the point Q. Since Q is a point on the root locus, we would have KQ to be equal to minus 1 by Cp evaluated at the point Q, and since we have one lumped pole near the origin and two poles P4 and P5 at some distance away from the origin, this would simply be equal to minus of PLQ times P4Q times P5Q, and this in turn is given by minus of magnitude of PLQ times e to the power j angle of PLQ times magnitude of P4Q times e to the power j angle of P4Q times magnitude of P5Q times e to the power j angle of P5Q, which can be simplified to be equal to minus of the magnitude of PLQ times the magnitude of P4Q times the magnitude of P5Q times e to the power j of the angle of PLQ plus the angle of P4Q plus the angle of P5Q. So this is going to be the expression. But since the point Q is a point on the root locus, we note that the sum of the three angles PLQ, P4Q and P5Q should be equal to minus 180 degrees, or in other words minus pi radians. So if we substitute that, we would get this to be equal to minus magnitude of PLQ times magnitude of P4Q times magnitude of P5Q times e to the power minus j pi. And we know that e to the power minus j pi is minus 1, and there is a minus 1 here at the start of this expression, and the two cancel one another, so that we get kq to be equal to simply the magnitude of PLQ times the magnitude of P4Q times the magnitude of P5Q. Now what is the magnitude of P4Q and P5Q? Since P4 and P5 are coincident poles, the distance of the point Q from the point P4 or P5 would be equal to root 2 times L, and that is because the triangle P4QPL is a right angled isosceles triangle and the sides of the triangle are both equal to L. So the hypotenuse will therefore be equal to root 2 times L. So if we exploit that fact, we would get that kq will therefore be equal to the magnitude of PLQ, which is going to be equal to L, times the magnitude of P4Q, which is going to be equal to root 2 times L, times the magnitude of P5Q, which is again going to be equal to root 2 times L, and hence kq is going to be equal to 2L cube. Now this gain kq should be greater than the maximum gain that the open loop system would achieve on account of the uncertainty that exists in the gain of the plant itself. Now when the plant gain reaches its maximum value, the closed loop pole position PCL will be at the point PCL max, and hence the gain K max of the overall open loop system when the plant's gain is at its maximum value is given by K max is equal to minus 1 by Cp evaluated at the point PCL max, and what is that equal to? That is equal to minus P1 PCL max times P2 PCL max times P3 PCL max times P4 PCL max times P5 PCL max, but since P4 and P5 are coincident poles, we would just have that to be equal to P4 PCL max the square divided by Z PCL max times Z bar PCL max. So this is going to be the expression. Now once again we can make a further simplification of this expression by noting that since the point PCL max is a point on the root locus, we would have the sum of the phases of the complex numbers P1 PCL max, P2 PCL max, P3 PCL max, P4 PCL max, P5 PCL max, and the difference of this sum from the phases of the complex numbers Z PCL max and Z bar PCL max, that net algebraic phase contributed by all these different open loop poles and zeros at the point PCL max will add up to minus 180 degrees. So we can write therefore K max as minus of the magnitude of P1 PCL max times P2 PCL max times P3 PCL max times P4 PCL max the square divided by Z PCL max times Z bar PCL max times e to the power j times the sum of all the phases, which as in the case of the point Q will end up adding up to minus pi radians. So exactly as in the previous derivation that we undertook a few minutes back, e to the power minus j pi is minus 1, and that minus 1 multiplies with the term minus 1 at the start of this expression and a 2 multiply to give us plus 1. Therefore k max will be simply equal to the term within this modulus sign, namely the magnitude of P1 PCL max times P2 PCL max times P3 PCL max times P4 PCL max the square divided by Z PCL max times Z bar PCL max. Now in this expression, since we know the point PCL max and we know the open loop pole positions P1, P2 and P3, the three terms P1 PCL max, P2 PCL max and P3 PCL max are known to us. So we can determine their magnitude without any trouble. Likewise, the term Z PCL max is also a term whose magnitude is known to us because we have already fixed the location Z of the controller 0, and we also know where the closed loop pole PCL max would be located with respect to the point Z, and likewise Z bar PCL max also is known because we have already fixed the locations of both PCL max and Z bar. So all these terms are known. The only term that is not known is P4 PCL max the square. Now what is that term? If we come back to the figure that we have here, we note that P4 PCL max refers to the distance from the point P4 to the point PCL max, and since the point PCL max is very close to the origin, the distance from the point P4 to the point PCL max is for all practical purposes equal to the distance of the point P4 from the point from the origin itself. Hence for all practical purposes we would have therefore that P4 PCL max is approximately equal to P4 PL, which is the lumped pole at the origin. So and this distance from this figure here is equal to L. So therefore we would have that K max is equal to the magnitude of P1 PCL max times P2 PCL max times P3 PCL max divided by Z PCL max times Z bar PCL max times L square, because the term P4 PCL max is equal to L square. So in order for our closed loop system to be stable, the gain at which the root locus crosses over from the left half of the complex plane to the right half of the complex plane should exceed the maximum gain that our open loop system would assume on account of plant parameter variations. So in other words, what we require therefore is that the gain K max should be less than the gain KQ. This is what is required of us. Now let us write out the two terms once again. The gain KQ is of course given by 2L cube, and gain KQ should be greater than K max in order for our closed loop system to be stable. So 2L cube should be greater than or equal to the magnitude of P1 PCL max times P2 PCL max times P3 PCL max divided by Z PCL max times Z bar PCL max times L square. And what this indicates therefore is that the distance L, which is the minimum distance at which the far away controller poles need to be placed away from the origin, is given by L should be greater than or equal to 1 by 2 times the magnitude of this term above, namely magnitude of P1 PCL max times P2 PCL max times P3 PCL max divided by Z PCL max times Z bar PCL max. Now if you plug in the values for PCL max and P1 and P2 and Z bar and P3 and so on, we would get that the distance L should be greater than or equal to 30. So our poles P4 and P5 should be at least 30 units away from the imaginary axis on the negative real axis of the complex plane. So the other step that is remaining as far as the feedback controller is concerned is to determine the gain of that controller. Now since we know that the point PCL0 is a point on the root locus, we can determine the controller gain by once again applying the root locus equation at the point PCL0. We know that our overall open loop gain K is given by minus 1 by Cp evaluated at the point PCL0. Since we have now determined the structure of our controller C, we know that our controller has 2 poles and 2 zeros. So it is going to be of the form S plus Z times S plus Z bar divided by S plus P4 the square. That is going to be the structure of our controller, and our plant nominally would be of the kind 1 by S times S plus 1 times S plus 2. So if we evaluate this entire thing at the point S is equal to minus 1.5 plus 2j, then we would obtain the controller gain K, and with that we would be done with the design of the feedback controller. If we compute the numerical value, we find K to be equal to 17,930. Therefore our feedback controller C is given by 17,930 times S plus Z times S plus Z bar divided by S plus P4 the square. We are now done with the second step of our control design. We have determined in the first step the locations of the zeros. In the second step we have determined the locations of the far away poles and used both these pieces of information to determine the overall feedback controller of our system. What is remaining is for us to determine the structure of the pre-filter. If you recollect, the purpose of a pre-filter is to cancel the effect of the controller zeros on the overall transmission function relating the reference to the output, and hence we would have to choose a pre-filter that has the terms S plus Z and S plus Z bar in the denominator. So we have fixed the denominator of the pre-filter by noting that the pre-filter is intended to cancel the open loop zeros, which are also going to be the closed loop zeros of our feedback system. And since we want our pre-filter to have unity gain, we choose the numerator to be ZZ bar, so that when we set S is equal to 0 in order to obtain the DC gain of our system, we see that the gain of our pre-filter would be 1. And with this we are done with 2 degree of freedom control design in order to achieve the specified amount of robustness of the closed loop system to the particular kind of variation we had in the plant parameters. I have shown in this graph the overall root locus of the system. So we have this plant whose gain K0 is uncertain. It can vary by a factor of 10, nominally it is equal to 1, but it can reduce to 0.3 and increase to 3. And in order to make sure that the variation in the closed loop pole, the dominant closed loop pole, due to the variation in the plant's gain is within 0.4 units, we need to have this as our feedback controller and that as our pre-filter. So if we zoom in near the origin, we will be able to look at the root locus in the vicinity of the plant poles P1, P2 and P3, and we see that indeed we have succeeded in placing the closed loop pole at minus 1.5 plus minus 2j as designed. And when we change the open loop gain by a factor of 3, we can show that the range of variation of the closed loop pole is also within 0.4 units. Now as a consequence of restricting the variation of the closed loop pole to within 0.4 units, we will also be able to accomplish a corresponding suppression in the spread in the transient response of our closed loop system when the plant's model varies, and that is revealed by the closed loop response of our system here, where we see that the response of our system when the gain is at its nominal value, and that is indicated by the blue trace here. So this is when K0 is equal to 1, and when the gain is at its maximum value, and that is indicated by the green trace here, and that is for the case when k naught is equal to 3, and the red curve here is for the case when k naught is equal to 0.3, and all of these three sit almost exactly one on top of another. In contrast, the 1 degree of freedom control design resulted in a response where the transient response was wildly different for the nominal case, which is indicated by the blue curve here, and the case when k naught was 0.3 and the case when k naught was 3. So this robustness that we have accomplished in the response of our closed loop system to variation in plant parameters is entirely due to our particular design of the feedback controller in combination with the pre-filter, and this was facilitated in a very transparent manner by using root locus as a tool for our design. Thank you.